So I want us to go on a journey. And our journey starts, as most do, with a question. How do we make programming better? It's a big question, one that I realized I've spent the better part of a decade trying to figure out. It all started back in the early 2000s. I was building websites in PHP, and nobody had heard of Rails yet, and so spaghetti code and sadness were kind of the lay of the land back then. And it was me and a friend of mine building these websites that were tens of thousands, even hundreds of thousands of lines of code, which was crazy at the time. And we eventually hit a wall. It felt like we were constantly writing the same crap over and over again. And there had to be a better way of going about this stuff. And so my first taste of what ultimately turned into an obsession came from building web frameworks. Because 10 years ago, it seemed like libraries and conventions and just raw discipline could make the whole thing so much better. And the truth is, for web programming, it did, right? This is, after all, what Rails brought to the table back then. And clearly, it had some form of success. But eventually, I got tired of building websites for other people. And despite my desperate attempts to end up on the .NET MVC team, I had to leave my web frameworking behind. And instead, I joined Microsoft as a program manager on Visual Studio. While I was at Microsoft, I sort of moved away from this code-oriented way of trying to think about this problem, and instead started to think about how tools could make the physical act of coding better. In many ways, you can think of it, I basically was trying to fix the mechanics of writing code. And during my time there, I designed and prototyped dozens of things that attempted to make that better. But more importantly, I had an opportunity to do something that only a handful of people have ever done. And that was, I got to sit behind a one-way mirror and watch people code and solve problems for weeks. And it was through this that I found definitive proof that it is not the mechanics that are holding us back. It's not that we can't write code fast enough. It's that we have to play computer in our heads most of the time. It's because we have this disjointed and slow feedback loop. And so I started to think about ways we could fix that. But unfortunately, priorities changed, and Microsoft wasn't really the right place for me to look into this stuff anymore. So I left, and I swore off DevTools for a while. I learned Clojure, and somewhat unsurprisingly, started building websites and web frameworks again. But then Brett Victor did his Inventing on Principle talk, and that poked the obsession. This time, it took the form of Lighttable, a tool designed to connect us to what we're creating and to get rid of that need to play computer in our heads. Now, in building Lighttable, we kind of started to push the boundaries of what our languages and platforms were originally intended to do. Right? The mainstream conception of programming just doesn't include things like true liveness, for example. And unfortunately, that's something that's particularly difficult to kind of shoehorn in after the fact. But that's what we set out to do. And I think we've done some really interesting work there. The latest versions of Lighttable really do help reduce the feedback problem. And so with that in place, it was time to watch people again, this time with Lighttable. And guess what? Even with immediate feedback, programming is still horribly broken. I went from frameworks to mechanics to connection. And in each case, it was an incremental improvement. It was a Band-Aid. It was then that I realized I made a classic rookie mistake. I set out to answer a question I didn't really understand. What is this really asking? It seems to suggest that there's something broken or inefficient about programming, but it doesn't actually say what. And even more fundamentally than that, it doesn't define terms. What is programming? Is it the act of writing code? Is it solving problems? Is it getting something to run on a computer? I wasn't sure. And to make this concrete, I needed data. So I did the obvious thing. I went and asked everyone I knew 2 questions. What is programming, and what is wrong with it? I asked beginners, I asked people who have been coding for a few years, and I had the opportunity to ask some of the best engineers in the industry. Anyone want to guess what I found, what I got out of that? Nothing? I did get more than nothing. I got wild variability. Say what? N+1 answers. Yes, that's true. No. I got wild variability and an incredible amount of complexity. The answers to what programming is were honestly depressing. I found out, not once did I hear that we are solving problems. Instead, I found out that we are plumbers and glue factories, that our lives are sort of mired in this caveat and frustration. And weirdly enough, that was the only common thread, which I guess is interesting unto itself, right? It sort of indicates that we as an industry don't seem to have an accepted definition for what programming is. But more interesting than that were the answers to the question, what's wrong with programming? They tended to fall in one of 2 categories. They were either so general and sort of like half-articulated that they weren't very useful, or they were so specific and tactical that they wouldn't apply to anyone else. So individually, the answers weren't very helpful in this case. But after talking to enough people, after getting into the hundreds of people I've talked to, some patterns did start to emerge in the aggregate. And after months of doing this, I finally came to a set of fundamental problems that we can use to sort of encompass all of our complaints. The first is that programming is fundamentally unobservable. So this one has been getting a lot of attention lately, thanks to Brett and the work we've been doing with Lighttable, right? We can't see what our code is doing. We can't see the effects of our changes. And we can't see how our programs are connected together. Sadly, that means that we can't really observe anything. The state of the art here is a stepwise debugger, which forces us to stop time, right? To stop the world and look at a single instant. And as most of this room probably knows, very few errors happen at a single point, right? It's through the observation of times passing that we actually find them. And for that, the best we have are print lines. We need to be able to observe the entire execution of our program, forwards, backwards, even branched into new futures, not just when a breakpoint hits. And interestingly enough, our industry seems to have accepted unobservability as a best practice. Think about a line of code like this. What does it do? Right? OOP's notion of encapsulation is by definition unobservable. Now, I have no idea what person.walk does. It probably does something sane, like set is walking to true, but it could also set 8 carrots to true, and it could have determined that I'm about to pass out from exhaustion. I have no idea and no way to tell. We are quite literally throwing darts in the dark and praying that we hit the board. We can't see what our programs do. And that's a problem whether you're a beginner or you've written millions of lines of beautiful code. Now, the second point is that programming is indirect, that everything we do is an exercise in translation. Even math, from which our programming languages are born, requires us to translate it into something like this. Why do we have to see that instead of this? And that's with something that translates fairly cleanly. What happens when it doesn't? all we get in code are symbols. We never see the real things. We never interact with the real things, just representations of them. And symbols are important, and they're powerful in some cases, but they don't have to be this opaque. They don't have to be this opaque, right? If I'm writing a card game, I should see this. Translation is hard. Using symbols is error-prone, especially when you couple it with operations on top of other symbols. And this indirectness, this inability to represent things meaningfully, is absolutely killing us. The vast majority of programming errors are translation mistakes. We had the idea in our head, but in trying to turn it into code, we just forgot something or made some silly mistake. Our programs are way too large to keep in our heads anymore. We need to be able to represent things meaningfully, and we need to be able to directly manipulate those representations. When we do math, we should do math in math. There's no technical reason we can't be direct. This last point is one that I think will really hit home with this crowd. And that is that programming is full of incidental complexity. And when I say that, what I mean is that there's all this crap that we do that has absolutely nothing to do with solving our problem. A perfect example of this is just think about how long it takes to get something simple to run on most platforms. Hell, we spend the better part of a week trying to set up a dev machine from scratch. And that's just one level of incidental complexity, sort of like a systems level of complexity. It's pervasive at every level of the stack, right? Code-wise, it seems the biggest thing we're running into right now is time management. And when I say that, most people immediately jump to concurrency or parallelism. And that's certainly part of it, but it's a lot more fundamental than that. Every time we add an event handler, every time we write a callback, we're doing time management. We're saying, at some point later, I want this code to execute. And now that our software is getting these much more complex interaction schemes, and we are seeing the proliferation of these multi-core systems, we're quickly realizing that callbacks are an awful solution to this particular problem. Every time we found ourselves manually managing something, we've built some system to do it for us. We were handwriting binary, and so we got Fortran. We were managing memory manually, and so we got garbage collectors. We were trying to encode data constraints, and so we got type systems. I think the next big step in terms of removing incidental complexity from code is automatically managing time. And we have to do this stuff. We have to remove these complex interactions that have nothing to do with our problems because we need to be focused on actually solving things, not solving the problems around solving our problems. We need to go from nothing to a solution in the time it takes us to think it up, not the months it takes us now. So there we go. These three things seem to encompass everything people had told me. And so we now have a framework for thinking about what's wrong with programming, which gives us a way of thinking about how to fix it. We just need to address these three things. The scary part is, though, that if you really think about it, the act of programming hasn't really changed in 50 years. Now, don't get me wrong, I know a bunch of you freaked out right there. We've gotten significantly better at it, right? We've created new languages, we've written new tools, we've raised the level of abstraction. But really, that just means we've gotten more efficient, right? We just keep pushing complexity around. And lately, there's been this murmur in the community of people starting to ask the question, why hasn't there been a stepwise change in programming? And I think the answer comes from the fact that every time we go and try and fix something, we focus on some local minimum and assume the rest is okay. We go, okay, we'll fix one of these, maybe two of them, and things will be so much better. And yes, that is true. Things do get better. I mean, after all, this is exactly what I've been doing, even with Light Table. But the best analogy I've heard for what this has resulted in is teacups stacked on top of teacups, right? Each time we go and we fix something and we push ourselves up a little bit, we make things better. But eventually those teacups start to lean. If we want to really change things, we have to look at the bottom. We have to start at the foundation and ensure that it solves our 3 big points. So how do we go about that? That's a big thing to try and do. Well, I think the first step is to come to a simplifying definition of what programming is. And the one I've picked is that programming is data transformation. Nothing else. It is not setting up systems. It is not setting up databases. It's not getting things to run. It is only taking data and turning it into other data. But instead of me trying to tell you what a world like that would be like, let me just show you. All right, so I said that this world I'm proposing only has data and transformation. And the use of data here is very, very important because data has a number of properties that automatically lend themselves to our original goals. One really nice thing is that you need very few kinds of it to actually represent most of the world, right? A vector with some strings in it can represent a to-do list, for example. A vector with strings and maps can represent HTML. You can create a header tag, and it's got a bunch of attributes in here, like class, and its class's greeting. We can even represent me. Take a map. I have a name. It's Chris. I also have a height. It's short. We don't need tons and tons of different types of things to represent the most of the world. It turns out that simply composing a relatively small subset of them, you can represent the vast majority of the things you want to. Another nice property of data is that it cannot change. You can only ever create new data, right? Data is fact. So if I create a map, and let's say I create a map up here, and it's got a counter as its key, and it has a value of 1. If I wanted to take this, and I wanted to increment the counter, or I just want to set it to 2, for example, I might click here, and I might set it to 2. But note that my original counter didn't change, right? Here's my new value. If I look at that, my original value didn't change. I can bring it back down here. All I've done is created a new value. And what this means is that data is by definition observable, right? All I have to do is capture the inputs and the outputs of any operation that I do, and I will see exactly what happened. There's none of this person.walk showing me or doing a bunch of things that I cannot see. So we have the fact that data can be composed into lots of interesting things, that it is fact, and so it is observable. Another nice thing is that data is pretty darn simple, right? I did a simple operation here. I wanted to change the value of a key. I changed it from 1 to 2. And I can change it to anything I want. I can change it to, whatever that number is, right? These operations on data, because they are so simple, are very easy to do directly, are very easy to start showing what's going on. I'm not writing code that sits there and changes this key. I'm just changing the key, and it's just doing the right thing. It's capturing the steps of what I'm doing. So let's see how you can do some maybe more interesting things, right? Because data, it just evaluates to itself, and that's not particularly useful. Let's create a vector here that has a bunch of numbers in it. And And so we've got our little vector of numbers. And like I said, it evaluates to itself. And in this little environment that I've created, the result of any step in this list is shown over here. And I'll make it a little bit bigger. I'll bring it down here so you can see what those are. Right? We have this vector of 1, 2, 3, and 4. So there are a very finite set of data of operations we can do on data. Another nice thing that it is, there are very few things that we need to be able to do. And so let's transform each number in this thing with some new set of steps. This green box says, hey, we're going to do stuff. And you can see the result of this is a vector that just has a bunch of nils in it. And that's because if we look at what do stuff does, it just returns nil. It's not very useful. So let's make it do something really simple. We'll just do some math here. We'll add 1 to the current value. And now we can see that we have a vector of 2, 3, 4, and 5. Now notice that I'm describing the steps of what I want to have happen, how I'm transforming data into other data. Unfortunately, though, not very many things could necessarily end in this world, right? We still need to do things that are side effectful. We still need to do things that are scary, that proliferate all the problems we see in programming now. So how do we handle that in a system where the world is only data? Well, the solution I have here is that we have an escape hatch. We have a way of passing data into something that can do the scary things for us. They're called transformers. And they're the way we'll handle state and the way we'll handle drawing to the screen and so on. But up until the point at which we need to do that scary thing, we're going to play in our world. And so to show this, let's write a little HTML out here, right? So we have this list of things, and we have a counter. Let's create a bit of HTML. We'll create a div. And we represent HTML in this world as kind of a tree of vectors, right? And we'll create a button, because what we're going to do is we're going to create a little bit of interface that allows us to increment that counter. So we want a map in here because we want to set something as click. And we want to set this as a pipe, basically a set of steps that we want to execute when we run that, or when we click on it. And we'll call this inc. So right now I have some data, and it represents HTML as far as I'm concerned, but it actually isn't HTML yet. Like I said, the last step we need to do is add a transformer. So we'll turn it into HTML. And you can see here, I'll zoom out just a little bit. I now have an inc button, right? And this is all wired up. Everything is sort of time managed for us. So as I change things, everything is changing for me. And now if I click on this, of course, nothing's going to happen because we haven't described what we want to do. And let's actually go up here just for a second. We'll rename these. So this is add 1, and this will be increment, right? And if we go in here, oops. I seem to have broken it. That's what I get. Let me refresh. All right, let me create that little bit of HTML again. So like I said, we have a div, and we have a button inside of it. With maps, click. Whoops. We don't actually want that to be that. All right, so we got our thing here. And what we're going to want to do is we're going to want to be able to take this map that we had before and increment it. So turn this into HTML. Got our increment button back. So I'm going to click on this, and you can see we don't have anything in here. We need to actually give this increment to our set of steps, or our counter map to our set of steps. And again, if we click on this, nothing's going to happen for us yet. But you can see we now have data what is in scope, right? We have data in this set of steps that we can then work with. And we don't want to return nil. What we want to do is we want to take this counter. Actually, no, sorry. We want to take this number, right? And what we want to do is we want to do some math on it. So, well, great. We're going to take this number, and we're going to add 1 to it. Right? We're just incrementing. That's all we're doing. And this won't do anything, right? If I click increment, it's not like that counter is actually going to go up, because we're not changing anything. We're just creating a new number. And so what we really want to do is create a new version of our counter thing. And we'll take the old result that we did some math on, and we'll drag it in there. And so now we have this wonderful new version of counter. But there's no state. Again, if I keep clicking here, nothing's going to happen. We need to use a transformer again. We need to say, hey, run this program again, but this time replace that value that I have for counter with this new one. And so now, every time I hit increment, you'll see the counter's going up. If we go back here, we can see that the counter's there. I can go and we'll actually just kind of add to our little bit of UI here. We'll create a span, and we'll add some placeholder value, and then we'll drag in this number. Oops. There it goes. And so now you can see every time I increment, I get another value, right? So what we have here is a way of playing in a world where there is only data, where we just do these simple operations. I like to think of this, right, when I did the vectors, I like to think of it as kind of drawing the data that I want, and then I just kind of drag and fill in bits of it. And then I feed that into a transformer, and it does the scary stuff for us. So that's great. I've shown you a little bit of state. I've shown you some sort of basic things. Let's do an example that's maybe a little bit more interesting. So my thought is we'll go through a standard data science workflow. I've gotten some data from a database. This is from Mongo. It's some usage data. And I need to clean it up. I want to do some math on it, and I want to draw a chart of the results. So the first thing we want to do is take a look at what our data looks like. We have a vector full of maps, and it has time and date. And what we're going to do is we're basically going to look at the average amount of time spent per day. So we need to get them in groups of date. Right? We want to see them, all the maps that relate to a specific day. And we can see, hey, we've got this map, and it's got all these keys for the days, and it has them there. We don't actually care about the days so much. What we really want is just the values, right? So we'll get the values of that. And so now we have a bit of data that looks like this. And so now we want to go over each of these things and do some math on them, right? So we'll do each, and we're going to do some stuff. And you can see we're getting just a bunch of nils. That's not what we want to be doing. So let's click on it. And so here's what the data that we're currently working on. This is the last iteration, if you will. And we want to get the time out of each one of these things. So we'll extract the value of time from all of this. And we have a nice little vector of all of the times. Now, I mentioned before, and part of the reason why I like the data science example is that we want to be direct, right? And I made a big deal about math. And I'm not a big math guy, and to be honest, I find math very opaque. But it's still nicer to do domains in themselves. So when we do math in this case, it knows that the previous value that you were working on was this array of numbers, or this vector of numbers. And so it gives me options to do math and math, right? I want to sum them. We can see the sum here. And then I want to divide that by the count. That's the mathematical definition for the mean. Great. So now if we go down and look at what we've got, we now have this nice little vector of numbers that are the averages of our daily usage. And I want to draw a chart. I'm not going to describe the code that's going to draw a chart for me. Not at all. I'm going to just drag some data on here and get a chart. And I can start modifying this chart. It's modifying underneath the structure, just a data structure that represents this chart. And so there you go, a data science example, straight the way through. And just out of curiosity, I wondered how long it would take me to do that if I didn't have to explain it. I could do all of this in 40 seconds. I dare you to try to do that in anything else. So the last example I wanted to do, I wanted to show you something a bit more complex, something that like a functional-oriented way of thinking about things doesn't really handle very well, something with lots of state. How many people here have seen to do MVC? Show of hands. Good, a lot of you, right? It's like the minimum viable, complete client-side website. And it does all sorts of little things, right? I can add new to-dos to this list. I can sit here and toggle them on and off. I can look at I can filter them and so on and so forth. Now, the point I wanted to make is that there's no difference between a running program and the data that's in a running program and the program itself, right? As I start clicking on these things, my environment is updating, because it's just representing what's on screen. And I can look and see how sort of some of these things work. If I look at how this remove completed button, this button down here, is shown, I'm basically saying, well, of all the to-dos that I have, match the ones where done is true. Right here, I'll make this a little bit bigger so it's a little bit easier to see. Match the ones where done is true, and then get the count of those, and then find a match for the count. If it's 0, well, we don't need to display a remove button. It doesn't make any sense. Otherwise, return some structure that represents the HTML for that button. Simple as that. And so this entire, to-do MVC is built up in this thing. And if I were to build this and the editor were a little bit better, right, this is very prototype, it would probably take me 5, at most 10 minutes to do it. Again, it's removing all of this incidental complexity. I didn't think about how to run it. I didn't think about how to set up databases. I didn't think about how to manage time. All of these things just happen because we're playing in a world that naturally fits our 3 original principles. And I know one of the points that people will probably bring up is, well, can this possibly scale? And I just want to point out, the editor itself, while simple in its sort of UI, actually has a pretty complex set of interaction, and it's all built this way itself. So I've shown you a system that is always observable, that is direct in every way that it can be, and that dramatically reduces incidental complexity. But I don't think what I've shown you is a tool. I think it's a medium, and there's a big difference between those two. A tool is something that allows you to be more efficient, right? A hammer allows us to more easily pound in a nail than a rock does. But something like steel is a medium. We couldn't have built skyscrapers with iron. It's just not strong enough. A medium allows us to do something that we just couldn't have done before, or that was impractical to do before. And interestingly enough, you can't know when a medium will enable. Programming is our way of encoding thought such that the computer can understand it and help us with it. So imagine what it would be like if we were finally free to focus on our problems. And by we, I don't just mean the people in this room. I mean everyone, not just programmers. What I've shown today is the beginning of Aurora, a new medium for thought. Thank you.